Thanks everyone for joining. I, Sanjib Hazarika, as Sir already presented, I have done my MTech in Energy Technology in 2003 and 2005. And currently I am working as a senior engineer in General Electric Limited. And as my profile mentioned, I mostly work for power plant and as well as gas turbine. And my current role is not the core design engineering, but somehow in a techno-commercial kind of stuff. Basically, I provided my information or some of the queries that the customer asked or some of the informations they required. So we provide those things to the commercial team, and then commercial discuss about those with our customer. So today I am going to present about decarbonization as well as the hydrogen for gas turbine operation and some information related to the energy scenario, also stuff related to emission, and also of course about the gas turbine. So when we talk about electricity, it's the heart of modern technology. Means without electricity, we cannot imagine about technology. Everywhere what we used or everything what we do is required electricity, almost everything. And here we have like a energy dilemma. That's basically the scenarios that involve to generate electricity. First thing is reliable. Electricity should be reliable, and means it should be available to everyone at all the time, not like an intermediate, but it's almost one of the universal requirement when we say about electricity. Second one is affordable. People should be able to buy that electricity and use it. If it is costly, then I think there will be limitation what it can be used or not. And then the last one is sustainable. It should be sustainable. It should be friendly to the environment. It should not impact socially or should not create too much problem to citizens or general population. So going forward, we can talk about electricity generation. These are basic informations. There are different type of electricity generation plant, we can say. Some are like fossil plants that may have gas as well as coal, and a lot of new renewable power plants are also coming. Then we have electricity production from hydroelectric power plant like dam. Then of course nuclear, and then we have others like a solar and wind turbines, and also geothermal energy. That's some of the plant is used by some countries, mostly in northern region of the globe, like Iceland or Norway. And other than that, biomass also used in some form for electricity generation. So going forward, this is a chart or presentation on the electricity production by different type of fuel, and it basically shows the latest data. Even 2021, fossil used to have a big share in overall global electricity production. It's still 61%. And if we see nuclear, wind, solar, this 35%, its a percentage is growing, but still it is a lesser or minor percentage compared to what fossil generates. There are others like biomass, other renewable like a small hydro plant, it's also contribute 3%. And on the right side, if we see what is the fuel used, is that coal is still the major part of electricity production, amounting almost like a 35%. And after coal, it's gas-based power plant. It's still 23%. And after that, we can see hydropower plant. It's a 16%. And then it's nuclear, 10%. And other than that, renewables, all those stuff, maybe around 10% if we combine wind, solar, as well as some small other renewables. So majority of electricity production, you can say, is still very much based on fossil fuel, and that's one of the problem for our especially for emission and all those stuff that we will discuss later. Moving forward, this is like a electricity generations over a period of time. It's showing from 1985 to around 2020. So on the bottom, it's still, as I mentioned, coal is still dominating overall global power generations. But you can see the trend for coal may be almost at a stagnation. It's not increasing too much, maybe last 5 to 7, 8 years. And after coal, it's gas, and still dominating or the second most important electricity generation sources. Then, as shown earlier, it's the hydropower, and then nuclear, and still we can say this renewable power is still the minor compared to the overall electricity generation in this world. And on the right side, it's basically showing the trend of each of the fuel. Here we can see overall percentage of coal in overall electricity production. It was decreased from around 37 or 38% to less than 35%. And gas is remaining same for last couple of years, maybe around 22, 23%. And this nuclear, actually there is a heavy drop of nuclear in percentage. That basically some of the nuclear power plant was shut down in last couple of years. For example, Fukushima in Japan, and that has a major accident and whole plant was shut down. And also I think in a lot of in part of the world, especially in developed countries, they are not installing new nuclear power plant. But still there are power plants installation going on in countries like China, India, or some other developing countries as well. And the bottom is that wind, solar, this renewable energy percentage-wise is growing, but still it will take a significant time to replace all the fossil power plant or the power generations that's currently happening. But it's expected that it will take quite a bit of time to meet all this requirement. So of course, coal is still dominating overall global electricity production, and it's mostly one of the reasons is China, where most of the electricity production or a large part of the electricity production is done by coal-based power plant. India, Australia, South Africa, they are very much rely on coal. US used to have a large fleet of coal-based power plant, steam power plant, but that percentage is reduced significantly in last 20 years, and a lot of coal-based power plant is replaced by gas-based power plant in US. But still we can say still coal is the dominant factor in electricity, overall electricity generation. On fossil fuel, we can say that it's a very high energy source and it's used for a very long time. And when we show still about the fossil fuel, it is coming to our mind about the coal, oil, as well as natural gas. And these are the three primary fossil fuel that we humans rely on for a long time. This is a slide that's basically gives some comparison between coal and gas. And coal power plant used to be happen maybe more than 100 years earlier. It's like an Edison plant that was established in New York in 1882. So it's like almost 140 years. And that's coal-based power plant is generating power. And here in this left side, it's showing a picture of a coal plant. And here is the process. Basically, it's a boiler where we burn the coal and it produces steam. And that steam is used to run a steam turbine. And that steam turbine used to run a generator. And generator used to produce electricity. This is the overall overall system for a steam power plant, and on the right side it is a gas-based power plant. One is the picture and is the cycle. Basically, gas-based power plant is mostly run by gas turbine. Gas is injected into gas turbine, and gas turbine produce electricity using a generator, and it also has exhaust gases, and that exhaust gas can be used in a waste heat recovery boiler or heat recovery steam generator we used to call. That again produces steam, and that steam can be used to run a steam turbine. So we'll discuss about this later. And in comparison for coal and gas, we can say that gas is far more cleaner fuel compared to coal. It produces almost like a 50 to 60% less carbon dioxide, 90% less carbon monoxide, almost 99% less sulfur dioxide, then nitrous oxide also comparatively very less, and particulate also very less compared to what is coal-based power plant used to have. So overall, if we compare coal and gas, gas has far more better benefit compared to coal from the emission point of view, and there may be other reason as well. But also it depends upon whether it's available or not, all those stuff. So still in India, even if we have so much advantage on gas, still majority of electricity production is based on coal because there is very less gas available in India. So that is a major factor. So it is again coal versus gas. It's like a carbon dioxide emitted per million British thermal unit. So here we can see coal almost like a 228 pounds emitted for MMBTU of it is of thermal units energy. So if we compare it, all these type of fuels, coal, then diesel, then gasoline, and also propane, and then natural gas, we can find that natural gas is far more cleaner almost among all the fossil fuel that can be used either in a coal-based power plant or gas-based power plant. So comparatively, it is a cleaner fuel. Moving forward, it is about the carbon emission. This on the left side, it's basically provide what is the atmosphere carbon dioxide concentration for over a century. I think it's like almost like 4 or 5 centuries. And this carbon dioxide in the atmosphere, I think that can be measured using sample of ice cores that was, I think, formed during that time. And I think it's basically measured using some ice from South Antarctica or South Pole, where ice are one form is not melted for a very long period of time. So here we can see the concentration remain almost similar, maybe around 270, 280 ppm over a period of very long time till the Industrial Revolution happened, maybe around 1800th century, 1810. It slightly increases, and from 1900th century, the increase on carbon dioxide concentration is steeper, and it's become very much at a very faster rate. We can say around 1950 or around during that time. So because of all new inventions and also a lot of other requirements like electricity as well as cars, transportation, all those things. And on the right side, basically is provide how much carbon dioxide emission by different sectors. And basically, if we see the topmost one, it's electricity and heat. It's the highest contributor of carbon dioxide emission, followed by transport sector, then the manufacture and construction sectors, then of course building, and there are others also that also contribute. But overall, the electricity and heat basically in some of these combined cycle power plant, they use this steam for directly for heating purpose. For sometimes it is a process industry like a chemical plant, or sometimes it's called district heating, means in some cold climate area they use directly those steam for heating of the houses. So it's mentioned as electricity and heat. So basically, you can say that electricity and heat contribute the major or the topmost carbon dioxide emission in this in overall. So we can move forward. So here come the decarbonization. Basically, last maybe 10 years to 15, 20 years, this decarbonization that requirement is picking up. One thing is the Paris Agreement that was happened in 2015, when it was committed that global warming to keep well below 2 degrees Celsius above pre-industrial level. So to meet the global this carbon dioxide emission requirement, that emission has to be reduced by almost like a 45%, and it has to be almost like a net zero by 2050. So this is the requirement that's actually coming up recently, and also we have I think a scope 26 meeting few weeks or few months back. So now it's very much required for every country to reduce their emission, and it's like developed countries, they are targeting 2050. I think India target is around 2070 to make it net zero. But to have this net zero target by 2050, every country has to start from now onwards to reduce the emission so that the target can be achieved. And how can it possible? So if we move forward, so one way will be to convert all the electricity production to renewable. But when we say we can do it, but in reality it is not so much easy. If we see from the industrial scale, it's not like some prototype or some experiment for a limited area or with limited requirement. But for a whole country to become a net zero, there are challenges from renewable energy. One is that it's not dispatchable. So we cannot turn on or turn off renewable energy whenever we want. Second one is intermittent and not well timed with demand. So demand requirement changes over a period of time. Even in the whole day also it will change. Morning demand may be different from what it used to be in evening. And then we have another technical challenges like a system frequency, demand exceeds supply, those kind of stuff. Then also integration of wind and solar plant into grid. That also very much depend how much percentage of electricity produced by wind and solar. Maybe at a very small scale, maybe 3, 4, 5% may not be an issue. But if we go for a very high percentage from the renewable, especially wind and solar, it may have some consequences on the grid, and grid able to take up those kind of variable load as well. And the last point is about the utility scale storage. Storage can solve some of those problems, but that's also is not technically, it's not viable at least at this point of time to have industrial scale storage where we can keep storage of a very high caliber electricity demand. So we can discuss these things in later. So these are the challenges from renewable. There will be other challenges as well, but it's like a high level. I'm just mentioning it. This chart actually provide about wind and solar integrating into a changing net load of a grid, you can say, and it's like a generic. I'm just showing it, and here we can see the topmost bottom one is the like a coal plant that is operate over a period of time, maybe in a day, from 1 to 24 hours. And then the second one is like a nuclear. The third one is maybe some others as well, some other plant, maybe small power plant, diesel engine, all those stuff. Then gas-based power plant is one of the major contributor on the overall power generations. And then the hydropower plant that's producing electricity. And then this yellow part is the solar. Solar is basically is depend on time of the day. It's like morning, maybe around 7 o'clock, it is started generating electricity, and it may be end by around maybe 7 or 8 o'clock. It's maybe slightly different for some countries where sunset may be at a later stage, maybe at 7:30 p.m. Not like India where it used to be around 6:30. So basically, that's the time period of solar energy generation. And the topmost is the wind power plant, which also varies depending upon the wind flow at a different time frame of the day. At certain period, it may be slightly higher, certain time it may be lesser. So it's about the net load. It's basically the load of the grid or the generation that minus solar and wind. So here we can see this is the net load. It's like if we say it's like 8,000 megawatt, it's hovering around that whole day. So going to next slide. Okay, so it's basically same what I shown you. This is the load of electricity from maybe around 12 a.m. at night to around 11, similar to 11 p.m. at night again. So we can see the demand of electricity increases around maybe morning time. It's a generic. It may vary to place also, session to session. Maybe winter it may be slightly different from summer, or in some countries it may vary. But it's a generic trend that used to happen. So it increases at morning, then again it slightly decreases, and evening time when people come back from offices and started lighting of the house and all those stuff, it again increases in the evening. So what happened? This is the normal trend, and when we have the below curve is the for solar. It's like when we have a solar electricity generation that start maybe around 7 a.m. and it's maybe up to maybe around 6 to 7 p.m. So the electricity demand or the net load from other sources, not minus solar, so it actually decreases. So because this requirement for this time period is catch up by solar electricity production. So the curve for other electricity requirement is decreases like this. So these things actually, if we see over a time period of time in the right side, maybe this is from a US state, I think it's a Florida or California. So what happened there? It's basically the electricity demand. It's in 2012 is like this. This is showing on the top. And what happened when we inserted more solar energy? The demand from other source other than solar, it started decreasing. So 2013 it's slightly lower, 2014 is more, it's going down, and 2020 is very much almost like a more than 6,000 megawatt, or almost like a 7,000 megawatt less than what it used to be in 2012 or 2013 time period. So what happened? It happening that the electricity demand from other electricity generation started lower or producing lower megawatt, maybe from 7 to 8 a.m. To maybe around 7 p.m. But after that, it required a significant increase in electricity demand because solar will not be there, and the other generation required to ramp up. It's a ramp up like a 13,000 megawatt in 3 hours time. So this curve is also called as a dark curve, as shown here, because it looks like a duct. So this actually create a lot of issue or problem for the whole grid. Actually, you require to restart a lot of fossil power plant, or whatever power plant is running at a lower load need to be ramped up. So that can be done up to a certain period. We cannot have so much electricity can be generated within so less time frame. And if this trend is continue, we either need to shift the demand to maybe at an early time, uh, not at 7 p.m., maybe maybe at the early time, as well as either other option is to stop solar generation. And then third one may be to that if we can storage that additional electricity and can be reused in later time frame. That is another option. And another additional option may be if we can use this extra electricity at this time to produce some environment friendly fuel like hydrogen by electrolysis or some other form, so that hydrogen can be utilized at a later stage to produce electricity. So that's one of the reason what actually asks people to think, how can we mitigate this high risks of producing additional solar energy during the daytime. So let me show you one grid. This is basically two grid system. One is with the left is 10% solar and wind energy, and the right is the 30% solar and wind energy in the grid. So talking about the left side, we can see how the electricity demand changes and how the electricity generation by different sectors changes at the time frame. We can see nuclear is basically almost remains same, because ramping up or ramping down nuclear power plant is not easy. Then the coal, and then gas, and the top is the solar, wind, and hydro and other. So the electricity requirement, when it increases, it is the gas and coal plant that take that load. Actually, they can be increased their capacity by producing more, or they can be reduced to generate less. So similar thing they can manage. And then they can mitigate the extra demand that required during the time frame. On the right side, that's basically a grid system that has almost like a 30% solar and wind energy. So here they don't have any coal plant. They get a small amount from nuclear, then hydro, and then a big chunk of their energy generation is from solar and wind. Then they have gas-based power plant. Also, sometimes they have option for import. So basically, in Europe, there are countries they can import or export their electricity, especially like Germany, Sweden, Denmark, even France, I think. So they can buy electricity from other countries if they feel that their demand is high. At the same time, if they feel that they have generating extra electricity, they can sell it others. So what happened here, you can see the electricity demand at certain point, the electricity production price, solar and wind, is quite significantly high, and it is reducing after some time. So the gas-based power plant try to make up whatever reduction happen in renewable, and also they have to import certain percentage of their electricity demand to meet their demand as well. So that's basically shows the grid system works. And if we increase the solar and wind percentage more, like a 50-60%, then also it will behave quite significantly different. They will have extra electricity during some of the time frame, and at some time frame they will have shortage of those electricity generation. So they have to have a system to mitigate those kind of risks. And to create a grid system, those will take significant time. So let's move again forward. This is about electric incentive industry like aluminum, iron, steel, cement. And in India, most of these industry used to have captive power plant. They have their own power plant. So in India, most of them have coal-based power plants. Some of them, like a petroleum, Numaligarh refinery has their own gas-based gas turbine power plant. So they used to maintain their electricity requirement within their plant itself. So when we go for a renewable, so they have to think how they make up their electricity demand using renewable. And these are very high incentive. Means if you require aluminum industry, it's required a lot of electricity. At the same time, it should have very much reliable. They cannot shut down their electricity requirement or electricity utilization. Maybe very short period of time. Maybe even 1 hour electricity outage may create huge losses to this kind of companies. So making or running a this kind of plant or this kind of industry in a renewable will be a huge challenge to mitigate, and it need to be find a way to do it. So there is another way towards zero carbon dioxide without maybe not relying 100% on renewable. Within maybe next few years or next few decades, maybe it should be at a slightly lower or slightly slower phase. So what we can do, we can go from coal to renewable directly. That will give like 100% less carbon dioxide, but it can be done when it is available or technically it is feasible. The second one is the coal to gas. We can transfer a lot of coal-based power plant to gas-based power plant, and that will automatically reduce the carbon dioxide emission by around 50 to 60%. Then the second thing is gas plus hydrogen. So hydrogen is a actually is a very pure fuel. We can say there is no carbon in it. So the carbon dioxide emission from hydrogen burning will be lesser compared to what is natural gas. But there are some technology challenges at this time. So basically, to go for a complete 100% hydrogen, so I'm mentioning that it is a gas plus hydrogen. So it again will produce less around 30 to 40% less carbon dioxide. So the last one is like gas plus hydrogen. Whatever gas turbines are operating, it can be converted to complete hydrogen. It will give almost 99 plus percentage less carbon dioxide, and it will be almost like emitting zero emission. It is keep 99 plus basically because in air also there will be a little bit of carbon dioxide. So when we burn this air and fuel together, so the gas turbine or the pan will produce slight, very minimal percentage of carbon dioxide as well. So it is mentioned around 99 plus, but it will be very small compared to what it used to be, at least for the coal power plant that is running currently. Yeah. So next phase is about combined cycle power plant. Basically, when we talk about gas turbine, it has to be a combined cycle power plant, or there are gas turbines that run in simple cycle as well, where water is not very much available. But it's almost like a gas turbine was linked with a steam turbine that actually both together produce electricity in a combined cycle power plant. And I think it's very much known to everyone that in a combined cycle power plant, they will have a topping cycle and a bottoming cycle. The topping cycle is basically the gas turbine part, where it used this fuel, natural gas fuel, and then it produces electricity through the generator, and then it produces waste heat or exhaust that is used in a waste heat recovery generator, and that ultimately used to run a steam turbine. Steam turbine also produces electricity, and of course there will be a lot of auxiliary system when we operate gas turbine or a steam turbine. You need to have a cooling system, Then whenever the gas turbine required to have combustion, it required oxygen. Oxygen means air, so their air need to be filtered. And also there are a lot of auxiliary systems that has to be maintained. So basically here in the here it shows two combined cycle plant. One is one gas turbine linked with one HRSG, or we can say that is the waste heat recovery steam generator that produces steam. So this is 1-in-1 configurations we used to call. And the top one is like there are two gas turbine that produces steam using this waste heat recovery steam generators, and this steam is used to run the steam turbine. So it's two gas turbine and one steam turbine, 2-in-1. So configuration. So this is basically a system of a combined cycle plant. We may have 3 steam generator as well as maybe 2 steam turbine. That's basically depends what is the customer requirement and how we optimize the combined cycle power plant to get the best performance, overall performance at that particular scenario. So this chart shows generic combined cycle plant energy utilizations. So when we say fuel to gas turbine, it's going. So gas turbines used to produce electricity. Its efficiency is around remains like a 37.4% is showing, but it's increasing, and gas turbine may have around 39-40% efficiency as well. So whatever exhaust gas is there, and this exhaust gas is goes to HRSG or heat recovery steam generator, and certain losses also happen in gas turbine, generator losses or some gas turbine other extra losses. In HRSG, it's basically used to produce steam, and subsequently there are losses, HRSG losses as well, surface losses, and also stack losses happen. So this steam used to produce steam turbine power, and that's basically produced by the steam turbine. And a major chunk of this energy went to condenser. Basically, in a steam turbine, we used to maintain vacuum in the low turbine part, so that we can use maximum utilization of the energy that's available. So this condenser used to have a low concentrated heat. So basically those are not very much usable to power generation. So overall, we can say that a steam turbine produce almost like a half of what the gas turbine produce in a power plant. So maybe in a high level terms, we can say if gas turbines are producing like 100 megawatt, so probably steam turbine can produce around 50 megawatt like that in this power plant. So this chart is showing about the capability of gas turbines currently General Electric have. In gas turbine, there are a lot of several companies, but if we see the market share, General Electric, then Siemens Energy, as well as MSI, that Mitsubishi. These are the 3 major players. There are other turbine manufacturers as well, like Ansaldo and other companies, smaller companies. But for power generation, that's called like a heavy duty gas turbine. So these 3 companies actually dominate the market share. And from GE, we have a fleet of from small like a 35 megawatt or maybe 34-35 megawatt to very big plant that's like a 571 megawatt. These are like very much depending upon the ambient scenario. I think this standard output is at ISO conditions, like around 15 degrees Celsius. So these are the simple cycle, means it's only the gas turbine capacity. So these are the 50 hertz units. Actually, there are two different configurations gas turbine that the manufacturer maintain. One is for 50 hertz market, and another is for 60 hertz market. Basically, that's for US as well as Saudi Arabia, and in Japan also. I think certain part of that country was with 60 hertz requirement. So here we can expect that maximum capacity of a gas turbine can go up to around 570. And the other competitor also used to have at the same range. It's not like a very much bigger gas turbines are available in the market right now. It's very much around 550 to 570 maximum capacity. And the bottom is like a combined cycle plant with one gas turbine and one steam turbine configurations. So if we see, it's a maximum is like a 840 megawatt we can expect, having 9SA kind of gas turbine. This is the latest design. 9SA is the latest design in this gas turbine technology. And for 9SA, it's a 9F. It's like a slightly lower capacity gas turbines. And then we have 13E2, 9E, then LMS 100. These LMS are like aeroderivative gas turbines. Basically, the principle of gas turbine and aircraft engine, jet engines are similar. So some of these gas turbines are designed using the technology or the core that was from aircraft engine. So these are called aeroderivative gas turbines. And if we consider a combined cycle plant with two gas turbine and one steam turbine, the maximum capacity can go up to as high as 1680 megawatts. This is a quite lot of electricity generation from a gas turbine. This is maybe sufficient for even a very, not a very big, but maybe a major city. So this actually, the gas turbines are designed as per the market scenario at what customer want. And basically, because whenever the gas turbine purchase order used to come, it's like open bidding. They send it to different competitor or gas turbine manufacturer, and everybody try to figure it out that they design gas turbines as per the requirement of their customers. So this is the overall gas turbine sizing, we can say, that is available, at least for G. And this is the principle of gas turbines that they operate. It's like a very much ideal situations. Like we have a compressor. Basically, this compressor used to suck air, and then it compress it. Then we put fuel into this into the compressor in a combustor, and when it burns, it expands, and then it goes to a turbine. And turbine actually used to expand it, and that actually goes to that shaft. This energy goes to the shaft, and ultimately it goes to the electrical generator. And one of the things in gas turbine is that the compressor is attached with the turbine, so it's the same shaft, and as a big chunk of that electricity, or not electricity, power produced by the turbine used to run the compressor. So it is the Brayton cycle. This is the P and PV diagram we used to call it. So it's basically compression, and then heat input here, then it's the expansion, it's out. So this is the ideal scenario, but in actual, it's not in the same way it's happened because of other factors as well. So it is again the right side, it is the TS diagram, temperature entropy diagram. So same thing is happening, a compression, then a heat input is going on, then it's an expansion, and that's coming back to the same point. So in this cycle, some of the things we have to take care of is the material limitation. So we need to figure it out how much maximum temperature it can cause depending upon what are the material available. And the second is cooling technology. For some of the material, we need to cool it because the temperature goes so much high that without effective cooling, the material cannot sustain. So those things are important, and optimum work means the part of how much work that this cycle will do very much depend upon what is the pressure ratio. Pressure ratio is nothing but how much the discharge pressure of that compressor is. So ratio is this at this point, what is the pressure and what is the pressure at the inlet of the compressor. That's called pressure ratio, and this ratio has very much important factor in overall efficiency or the performance of this Brayton cycle. And this is shown as the ideal cycle, but in reality, there will be efficiency will not be as whatever shown here. compressor expansion efficiencies. So it will not be like ideal, whatever shown here. Then pressure losses will be happening, and then there will be leakage in flows here and there. So it will sit in some way. So we are not going so much detail on Brayton cycle, but this is a gas turbine. How it's look like. The top one is the cross sections view, and the bottom one is like a from a DCS how it's look like when it's see. So here we can see this is the inlet of the compressors. So when it started compressing, the gas temperature also slightly increases, and it goes to a combustor. This is a combustor sections. It will have a bunch of combustor cans. It's a circumference, and then when it started burning, it goes to the turbine sections. These are, I think, they have four stages in these turbine sections, and ultimately it will go to the exhaust column, and then it will go outside of the gas turbine. So on bottom part actually is showing how that gas turbine run the generator. This has this gas turbine speed around 5,236 RPM. So there are gas turbines that is with variable speed as well. And some of the gas turbine, the RPM need to be reduced to maintain like a 50 or 60 hertz. That's required for a bridge system. For 50 hertz, the RPM is typically 3000 RPM, and for 60 hertz, it is 3600 RPM. So here in this shaft, the RPM is around 5236 RPM. So this is the basic gas turbine. If we see the T part, compressor, combustor, and turbine. So this, other than this part, the gas turbine has a very complicated or complex cooling system. As I mentioned, the cooling temperature of gas turbines, the temperatures of the gas turbine after combustor used to be very high. So for those high temperature, we need a very sophisticated cooling system. So typically what happened, the compressor, some part of the compressed air is used to cool different section of the gas turbine, especially the turbine section. So it extracted from different point of the compressors, depending upon what is the requirement and at what pressure it is required and how much cooling will it required to be do. So cooling is everywhere in the gas turbine. I mean, it has to cool the rotor, it has to cool the diaphragm. Diaphragm is nothing but the stationary part of the gas turbine, and then it has to be cool the bucket as well. Buckets are the rotating part of this gas turbine, where actually energy converted into this to run that rotor. So here it is showing what are the coolings as bearing seal. Those also need to be cool. Then certain part of air need to be extracted to cool the low pressure turbine. That is the end part of this turbine. And it has several stages in the turbine part. It's the first two stages here. There are another 3 stages in the later part. So it's basically different design. So we need to have cool the hot gas part, means high pressure turbine section as well here. And that also depend the blade, like a second stage blade, then the first stage blade. First stage blade required more cooling, because here temperature will be higher than what it used to be here. And if we see in the bottom part is showing even the bucket, there are holes that can be used for cooling the buckets. And these coolings are very much important to overall gas turbine performance, because when we increase when we extract air from the compressors, ultimately means we are losing some of our energy. Otherwise, those energy will be used to produce more more either electricity, or it will go to the shaft. But here we are using it for cooling purpose. And how we optimize that extraction actually also depend very much how much efficiency this gas turbine is. And if we extract more air, the efficiency will be lesser. And if we stop extracting, or if we less, then the parts will be damaged because of the high temperature. So that has to be taken care. So it's giving some benefit of the gas turbine. So here, this is from a MSI brochure. It's available. Basically, here we can see. Here they have a called J series gas turbine, and the temperature at inlet to the turbine section can go up to 1600 degrees Celsius. That is a very high temperature, and I think a lot of metal will melt at that particular temperature. And the claim is that this temperature, the combined cycle efficiency go up to around 64%. That's like a very high efficient combined cycle plant. And going through the advantage of gas turbines, basically, if we compare with other plants, the installation and maintenance cost of a gas turbines are very less compared to less. As a combined cycle efficiency is significantly high, emission is reduced or lesser, and gas turbine has a very much fuel flexibility. It can run on gas, naphtha, diesel. Some of the gas turbine can also operate at furnace well. Then hydrogen can also be used. And then synthetic gases, that's basically gases that's coming from blast furnace, or some gases that used to come from process industry that also has some kind of energy that can be used to produce heat. Another is the startup time. Gas turbine can start up maybe half an hour if we require, without thinking about the bottoming cycle or the steam part. Ramp rate is nothing but that increase or reduction of output. That's very much flexible in a gas turbine. And the last one is the turn down capability. Means if we have a gas turbine of around 100 megawatt, we can run maybe around 30 megawatt as well. And at 30 megawatt, we can run continuously, and it will not violate any emission requirement of that particular area or particular locality. So there is quite a flexibility in the gas turbine compared to some other power plant as well. Moving to here, hydrogen, basically I'm not going into details. We can have different type of hydrogen depending upon how it is produced. Green, pink, red, all those stuff. Green is the actually most sorry, emission compliance, or we can say very much environment friendly hydrogen production that use renewable energy and water electrolysis to produce hydrogen. So it does not produce any kind of carbon, and also of course pink also very much environment friendly, but it uses nuclear power that is mentioned here. So in case of a gas turbine, when we talk about decarbonization, we can do it by two ways. One is the pre-combustion. We can use like a fuel that has zero carbon, maybe hydrogen. And another is the post-combustion, where we can remove the carbon from the exhaust of the gas turbine. Here we are going to discuss about the pre-combustion, basically the hydrogen as a fuel. Not any specific on the post-combustion part. So this is again the same thing what we discussed. It's specific to gas turbine. So how much the carbon emission we can reduce if we go from a coal that's a coal-based power plant to a complete new or the latest gas turbine technology with pure hydrogen. So currently we have carbon emission in the range of around 1000 gram per kilowatt per unit. So we can reduce it by around 45%, maybe with gas. Then with a high efficient, like a type of combined cycle plant, so we can reduce it to 60%. Then with the current technology, having capability to operate with 50% hydrogen. So it's mentioning because there are complexity to run a gas turbine with 100% hydrogen. for some of the gas turbine, how it is designed, how combustion works, that we'll discuss later. So with 50% with current technology, we can reduce it to almost like a 70%. Then we can have like a carbon capture, that is like we can remove the carbon that is available in exhaust by using some technology, and we can reduce it to maybe around 97% from what we used to be here. And ultimately with 100% hydrogen, we can almost remove all the carbon from the GT exhaust. So this is a pathway that can be achievable with technology. And these two curves actually shows the carbon dioxide emission and hydrogen methane as a fuel. So in the x-axis here below, it's the methane percentage. Methane is nothing but a natural gas, we can say, because in a natural gas composition, most of the part is methane, maybe 85%, and in some cases 90% as well. On y-axis, it is the carbon dioxide reduction. So it is this left side curve is by volume, and the right side is same based on the heating content. Basically, if we consider a heat for both methane as well as hydrogen, what it will be. So basically, we can say if by volume, if we reduce the to reduce 50% carbon dioxide, we require almost like a 75% by volume hydrogen, because hydrogen is lighter compared to methane, so its volume requirement is higher. But if you go with a heat content numbers, it's like a 50-50%. If you want to reduce carbon dioxide by 50%, we require a fuel that has 50% hydrogen. Or we can blend 50% hydrogen with 50% methane to reduce the carbon dioxide emission by around 50%. So these are some of the gas turbine that is available. I provided from General Electric company, and another is from Siemens Energy. And they also have quite similar to gas turbine that General Electric has. And what are the capability of gas turbines to burn hydrogen? So there are some complexity, as mentioned, that 100% hydrogen is still not very much possible for some type of gas turbine, especially the latest bigger gas turbines, because of certain complexity that we will discuss. So in I think a lot of gas turbine can go operate almost like 100% with hydrogen fuel. And the latest technology having AC class that can operate around 50% hydrogen by volume. Similar to Siemens, there are bigger gas turbines like SGT5 that can operate with around 50%. And some small gas turbine can goes up to 100% or 75% as well. And almost all the companies are trying to achieve 100% hydrogen burning capability of their gas turbines. And that is almost doing R&D, research and development in this field. So this is a case study that I just written here. Basically, is nothing but a calculation at a high level. If we have a 680 megawatt combined cycle plant, so basically how much hydrogen is required to produce that hydrogen, green hydrogen, how much renewable will be required, and what will be the water requirement if we go with the electrolysis process. So if we see 680 megawatt is the plant generation, hydrogen requirement for hour is around 34 tons. Then electricity requirement to produce that hydrogen is around 1,870 megawatt. As renewable has a lesser capacity factor, load factor, I just assume it like a 50%. That is also very much optimistic. So we will require the installed capacity of around 3,740 megawatt. So this is a big, huge numbers of installation capacity. So that's basically one of the challenges to produce so much hydrogen to run such a power plant like a utility scale. And also the water requirement is like around 306 tons per hour water requirement for the electrolysis process. So there are of course very big challenges to use hydrogen in a gas turbine. But yeah, of course, it's it's not unachievable, but challenges are there to have those kind of technology that can be utilized. So here also these challenges of hydrogen as a fuel. These are like a properties between methane and hydrogen. As I mentioned earlier, methane is almost like a natural gas that used to run for the gas turbine. There are significant difference for some of these properties. One is the flame speed. That's very much required for combustion. Also upper flammability limit, and this is also very much different. And also we can say this heating value, if we consider it like normal meter cube stuff, because of this mass of hydrogen, this is also significantly different. It's like almost 1/3 of methane. So ultimately, when we have a gas turbine burning hydrogen, we have to take care of all these scenarios of differences between hydrogen and methane, because gas turbines are mostly optimized to operate with natural gas. And when fuel is a different properties, the requirement for air that's required for combustion also will be different. And accordingly, the other component of gas turbine will behave or provide a different kind of complexity to be taken care. So below is that some of other complexity and NOx. I will discuss that in the next slide. Then combustion dynamics, how we burn that hydrogen at the particular temperatures, unburned hydrocarbons, then flashback. That's also mostly related with combustion of hydrogen fuel. And at the same time, as these gas turbines, when we do all those utilization to operate the hydrogen, at the same time we have to require to check whether we have this market for those kind of technology or not, because market is depend upon cost, how much customer is ready to pay, then of course efficiency, then the parts of the turbine, because most of the gas turbine or almost all gas turbine has a part designed for a specific time. After certain time frame, the parts need to be replaced, and that parts actually ultimately the cost of that parts goes to customer. So customer look that effect also flexibility. And then I think this is last one is maintainability. So is there any complexation to maintain those operation as well? So those also need to be looked into. And when we see these fuel properties, there are certain specific changes will be required in the field of combustion. This is the and fuel system, because of the volumetric flow of the hydrogen compared to natural gas, and also safety systems because hydrogen is more flammable. Okay, so the same thing what I mentioned earlier, the fuel systems need to be looked into, or there are certain changes will be required because volumetric heating value of hydrogen is almost like 1/3 of methane. So ultimately we require to allow to go more hydrogen to the gas turbine to maintain same kind of megawatt. So that actually requires changes in the fuel system or fuel piping, valves, all those things. Second one is the hydrogen smaller molecules. So in some of the component or some of the gaskets where the methane cannot pass, the hydrogen can pass. So that also need to be looked into. That's very important from safety point of view. So those kind of things also need to check. And the third one is the hydrogen has the ability to diffuse into some solid material, include some steel alloys. So that also need to taken care with technology. So it's called hydrogen embrittlement. And the second system is the combustion system. Of course, that's very much important from the combustion point of view. And some of the changes or design changes will be required in combustion system as well. And one point is the NOx. NOx is nitrogen oxide. So when we do some combustion at a very high temperature, the nitrogen and oxygen reacts and produce nitrogen oxide. And most of the government has very strict regulation across the world on how much NOx a power plant can produce. It says typically 15 ppm or 25 ppm. So when we burn so much hydrogen, we need to take care of that as well. So typically, when we have more hydrogen, the NOx levels goes high. So there are technology from a design point of view, how the combustor is designed. At the same time, there are other technologies like steam injection that can be done in the combustor to reduce NOx. But when we do those external suppression method like steam or water injection into the combustor, it actually impact the overall plant performance as well. So all our trade-off need to be looked into. The other challenges are like a storage. Hydrogen is more flammable, so storage may be a problem. Then again, transportation, that also need to be challenges that need to look into. So the last slide is that we can say that for this global effort for decarbonization, there are multiple pathways to achieve it, and one of the way to achieve this decarbonization or zero emission to have gas turbines that can operate with maybe zero carbon fuel like hydrogen. And this basically mostly important during the transition phase till we have technology that's available for 100% renewable for that can be utilized for utility scale. So this is the last page, and if we have any questions or that anybody has any comment that we can discuss.